हेलो दोस्तों, आज हम आपको समझाएंगे डायोड के टाइप्स और डायोड के आइडेंटिफिकेशन के बारे में।
तो वीडियो शुरू करते हैं। Diode identification. There are many types of diodes varying in size from the size of a pinhead used in sub-miniature circuitry to large 250 ampere diodes used in high power circuits. Because there are so many different types of diodes, some system of identification is needed to distinguish one diode from another. This is accomplished with the semiconductor identification system. This system is not only but for transistors, many other special semiconductor devices as well. The system uses numbers and letters to identify different types of semiconductor devices. The first number in the system indicates the number of junctions in the semiconductor device and is a number 1 less than the number of active elements. Thus 1 designates a diode, 2 designates a transistor which may be considered as made up of 2 diodes, and 3 designates a tetrode, a 4-element transistor. The letter N following the first number indicates a semiconductor. The 2 or 3-digit number following the letter N is a serialized identification number. If needed, this number may contain a suffix letter after the last digit. For example, the suffix letter M may be used to describe matching pairs of separate semiconductor devices. Or the letter R may be used to indicate reverse polarity. Other letters are used to indicate modified versions of the device which can be substituted for the basic numbered unit. For example, a semiconductor diode designated as type 1N345A signifies a 2-element diode 1 of semiconductor material N, that is an improved version A of type 345. When working with these different types of diodes, it is also necessary to distinguish one end of the diode from the other, anode from cathode. For this reason, manufacturers generally code the cathode end of the diode with K plus cath, a color or dot or band, or by an unusual shaped raised edge or taper. In some cases, standard color code bands are placed on the cathode end of the diode. This serves two purposes. L, it identifies the cathode end of the diode, and 2, it also serves to identify the diode by number. For example, a diode with brown, orange, and white bands at one terminal and figure out its identification number. With brown 1, orange 3 and white 9, the device would be identified as a type 139 semiconductor diode, or specifically 1N139. Types of diodes. This section will provide a detailed discussion of the operation and characteristics of many common diodes in use today, including the ZENER diode, silicon diode, photoconductive diode, light emitting diode, power rectifier diode, SCHOTTKY diode, varistor and VARACTOR diode. A discussion of silicon controller rectifiers thyristor will take place later since it more closely resembles a transistor. ZENER diodes. Diodes can be designed with a ZENER voltage. This is similar to avalanche flow. When reverse biased, only leakage current flows through the diode. However, as the voltage is increased, the ZENER voltage is reached. The diode lets current flow freely through the diode in the direction in which it is normally blocked. The diode is constructed to be able to handle the ZENER voltage and the resulting current, whereas avalanche voltage burns out an ordinary diode. A ZENER diode can be used as means of dropping or regulating voltage. It can be used to step down circuit voltage for a particular application, but only when certain input conditions exist and are constructed to handle a wide range of voltages. Signal diodes. A signal diode is a small nonlinear semiconductor typically found in electronic circuits where high frequencies or small currents are involved, such as television and radio signal processing, and digital logic circuits. The PN junction is usually encapsulated in glass and it has a black or red band at the cathode end. Signal diodes have lower current, that is 150 mA, and power ratings, that is 500 MW, than rectifier diodes, but function better in high-frequency applications or in clipping or switching circuits that deal with short-duration pulse waveforms. Signal diodes can be made of either silicon or germanium diodes. Germanium signal diodes have a lower forward voltage drop 0.3 V across the PN junction than silicon signal diodes 0.7 V, but have a higher forward resistance. Silicon diodes have higher forward current and higher reverse voltage peak values. The most common sizes for signal diodes are those rated with a maximum reverse voltage of 100 V, 120 V, 150 V and 200 V. PHOTODIODES. Light contains electromagnetic energy that is carried by photons. The amount of energy depends on the frequency of light of the photon. This energy can be very useful in the operation of electronic devices since all semiconductors are affected by light energy. When a photon strikes a semiconductor atom, it raises the energy level above what is needed to hold its electrons in orbit. The extra energy frees an electron, enabling it to flow as current. The vacated position of the electron becomes a hole. In light-sensitive diodes, often called photodiodes or photocells, this occurs in the depletion area of the reversed biased PN junction, turning on the device and allowing current to flow. The light striking the photodiode causes current to flow in the circuit, whereas the diode would have otherwise blocked it. The result is the coil energizes and closes another circuit, enabling its operation. Thermal energy produces minority carriers in a diode. As the temperature rises, so does the current. Light energy can also produce minority carriers. By using a small window to expose the PN junction, a photodiode can be built. When light fall upon the junction of a reverse biased photodiode, electrons hole pairs are created inside the depletion layer. The stronger the light, the greater the number of light-produced carriers, which in turn causes a greater magnitude of reverse current. Because of this characteristic, the photodiode can be used in light-detecting circuits, such as proximity detectors and fiber optic data bus receivers. Light-emitting diodes. Light-emitting diodes (LEDs) have become so commonly used in electronics that their importance may tend to be overlooked. Numerous avionics displays and indicators use LEDs for indicator lights, digital readouts, and backlighting of liquid crystal display (LCD) screens. LEDs are simple and reliable. They are constructed of semiconductor material. In a forward bias diode, electrons cross the junction and fall into holes. As the electrons fall into the valence band, they radiate energy. This is true in all semiconductor materials. In most diodes, this energy is dissipated as heat. However, in the light-emitting diode, the energy is dissipated as light. By using elements such as gallium, arsenic, and phosphorus, an LED can be designed to radiate colors such as red, green, yellow, blue, and infrared light. LEDs that are designed for the visible light portion of the spectrum are useful for instruments, indicators, and even cabin lighting. The advantages of the LED over the incandescent lamps are longer life, lower voltage, faster on and off operations, and less heat. Common LED colors in the semiconductor material that is used in the construction of the diode. When the diode is forward biased, the energy given off is visible in the color characteristic for the material being used. The anatomy of a single LED, the symbol of an LED, and a graphic depiction of the LED process. LEDs are used widely as power on indicators of current and as displays. For pocket calculators, digital voltmeters, frequency counters, etc. For use in calculators and similar devices, LEDs are typically placed together in 7-segment displays. This display uses 7 LED segments, or bars labeled through G in the figure, which can be lit in different combinations to form any number from 0 through 9. All anodes in a display are internally connected. When a negative voltage is applied to the proper cathodes, a number is formed. For example, if negative voltage is applied to all cathodes except that of LED A, the number 9 is produced. If the negative voltage is changed and applied to all cathodes except LED B, the number 9 changes to 6. 7-segment displays are also available in common cathode form, in which all cathodes are at the same potential. When replacing LED displays, one must ensure the replacement display is the same type as the faulty display. Since both types look alike, one should always check the manufacturer's number. LED 7-segment displays range from the very small, often not much larger than standard typewritten numbers, to about an inch. Several displays may be combined in a package to show a series of numbers. Power rectifier diodes. The rectifier diode is usually used in applications that require high current, such as power supplies. The range in which the diode can handle current can vary anywhere from 1 ampere to hundreds of amperes. One common example of a series of power rectifier diodes are those with part numbers 1N4001 to 1N4007. The 1N indicates that there is only one peta-Newton junction, or that the device is a diode. The average current carrying range for these rectifier diodes is 1 ampere and they have a peak inverse voltage between 50 volts to 1000 volts. Larger rectifier diodes can carry currents up to 300 amperes when forward biased and have a peak inverse voltage of 600 volts. A recognizable feature of the larger rectifier diodes is that they are encased in metal in order to provide a heat sink. Schottky diodes. A Schottky diode is designed to have metal, such as gold, silver, or platinum, on one side of the junction and doped silicon, usually an N-type, on the other side of the junction. In this respect, it is not a pure semiconductor diode. It is a metal semiconductor diode. A Schottky diode is considered a unipolar device because free electrons are the majority carrier on both sides of the junction. The Schottky diode has no depletion zone or charge storage, which means that the switching time can be as high as 300 MHz. The typical PN semiconductor switch is much slower. When an opposite voltage to the voltage supply that forward biases a PN junction diode is applied, current in the diode continues to flow for a brief moment. This time is measurable and is known as reverse recovery time. Schottky diode reverse recovery time is much shorter, which makes it suited for use in high-frequency rectification. It also has a very low voltage drop, 0.15 volts versus 0.7 volts for a silicon diode. Varistor. A varistor is not exactly a semiconductor diode. It is typically made of a ceramic mass of zinc oxide grains in a matrix of other metal oxides. This material is sandwiched between two metal plates which are the electrodes. The numerous grains form diode relationships with other grains so that current flows in one direction only through the device. The current-voltage relationship is nonlinear. A small or moderate amount of voltage applied to the varistor causes very little current flow. However, when a large voltage is applied, the effective junction breaks down and large current flow follows. Therefore, the varistor has high resistance at low voltage and low resistance at high voltage. Varistors are often used to protect circuits against excessive transient voltages. They are incorporated so that, when triggered, they shunt the current created by the high voltage away from sensitive components. Varactor diodes. The varactor diode, or varicap, is a diode that behaves like a variable capacitor. Its capacitance is dependent on the applied voltage. The PN junction functions like the dielectric and the NNP materials like the plates of a common capacitor. Understanding how the varactor operates is an important prerequisite to understanding field effect transistors FETs surrounding the junction of the PN materials is a narrow region void of both positively and negatively charged current carriers. This area is called the depletion region. The size of the depletion region in a varactor diode is directly related to the bias. Forward biasing makes the region smaller by repelling the current carriers toward the PN junction. If the applied voltage is large enough, about 0.5 volt for silicon material, the negative particles will cross the junction and join with the positive particles. This forward biasing causes the depletion region to decrease, producing a low resistance at the PN junction and a large current flow across it. This is the condition for a forward biased diode. On the other hand, if reverse bias voltage is applied to the PN junction, the size of its depletion region increases as the charged particles on both sides move away from the junction. A high resistance between the terminals and allows little current flow, only in the microampere range. This is the operating condition for the varactor diode, which is nothing more than a special PN junction. The insulation gap formed by reverse biasing of the varactor is comparable to the layer of dielectric material between the plates of a common capacitor. Furthermore, the formula used to calculate capacitance C can be applied to both the varactor and the capacitor. C equals AKD, where A equals plate area, K equals a constant value, D equals distance between plates. In this case, the size of the insulation gap of the varactor, or depletion region, is substituted for the distance between the plates of the capacitor. By varying the reverse bias voltage applied to the varactor, the width of the gap may be varied. An increase in reverse bias increases the width of the gap D, which reduces the capacitance C of the PN junction. Therefore, the capacitance of the varactor is inversely proportional to the applied reverse bias. The ratio of varactor capacitance to reverse bias voltage change may be as high. A reverse bias of 3 volts produces a capacitance of 20 picofarads in the varactor. If the reverse bias is increased to 6 volts, as shown in view B, the depletion region widens and capacitance drops to 5 picofarads. Each 1 volt increase in bias voltage causes a 5 picofarad decrease in the capacitance of the varactor. The ratio of change is therefore 5 to 1. Of course, any decrease in applied bias voltage would cause a proportionate increase in capacitance as the depletion region narrows. Notice that the value of the capacitance is small in the picofarad range. In general, varactors are used to replace the old-style variable capacitor tuning. They are used in tuning circuits of more sophisticated communication equipment and in other circuits where variable capacitance is required. One advantage of the varactor is that it allows a DC voltage to be used to tune a circuit for simple remote control or automatic tuning functions. One such application of the varactor is as a variable tuning capacitor in a receiver or transmitter tank circuit. An ohmmeter can be used to check a varactor diode in a circuit. A high reverse bias resistance and a low forward bias resistance with a 10:1 ratio in reverse bias to forward bias resistance is considered normal. Thanks for watching this video.
दोस्तों, फिर मिलेंगे अगले वीडियो में। कृपया इस चैनल को सब्सक्राइब जरूर करें। नमस्कार दोस्तों।